Okay, in this video we are doing Calc AB Problem Set 73. The problems and a playlist are in the description below. Let's do some problems. All right, we want to evaluate the integral of the quantity x plus 5 times the quantity x plus 3 cubed dx. This is potentially a very annoying problem because you can't integrate x plus 5 and integrate x plus 3 cubed and then just multiply those. It doesn't work that way. One option is certainly to expand everything, but that seems really annoying, although that will definitively work. So if you're not sure what else to do, dive in with that. What I'm going to choose to do instead, and this will work frequently, I'm going to let u equal the thing to the highest power. So I'm going to say u is equal to x plus 3. And now I need to reframe the entire problem in terms of u. So definitely du is equal to dx, which is great. But I also need to deal with this x plus 5. So I know because u is equal to x plus 3 that x is equal to u minus 3, which means that if I add 5 to both sides of that, I'll have x plus 5 is equal to u minus 3 plus 5, or u plus 2. So I can actually rewrite the entire thing now. So I'm going to say it's u plus 2, which is what x plus 5 became, and then x plus 3 became u, and then dx became du. So this is good. This I'm very willing to expand, right? This is just going to be the integral of u to the 4th plus 2u cubed. That's fine. Reverse power rule, so it's plus 1 times the reciprocal. So we get this, plus 1 times the reciprocal. You get 2 over 4, so that should definitely say 1/2. Error. Unfortunate. Okay, hold on. I'll fix it. This should be 1/2. I don't have the right color up, but we'll go with that. Okay, so we got this. And then u is equal to x plus 3. So I'm just going to make the substitution. And I get this. But of course, this 4 should really be a 2. And we get that. And I think that is the answer corrected. Hopefully, if not, let me know in the comments. Although I think it's right. All right, but you can see every once in a while I make a mistake. It happens, right? It doesn't mean we don't know calculus necessarily. It just means, when you end up doing 1,000 algebraic things to answer, 200 calculus problems, you're probably going to make a mistake here and there. And not calculus, you just live with it. Not a big deal. All right, we want to evaluate the integral of x plus 1 over the square root of x squared plus 2x plus 5. Our hope is that we can just let u equal the thing inside the radical in the denominator. So I'm going to start with that. U is x squared plus 2x plus 5. I will take the derivative or find the differential here. So du, I'm going to do in parentheses 2x plus 2 and then dx, because really everything gets a dx on the right hand side. It would be like 2x dx plus 2 dx, but factor the dx out. That's what most people do. So we have this. There is kind of an issue because in the original we only have x plus 1. We don't have 2x plus 2. It's very easy to turn 2x plus 2 into x plus 1. That's by dividing everything you see by 2. So that's what I'm going to do. So 1/2 du is the quantity x plus 1 dx. And now we're ready to make our substitutions. So x plus 1 and dx becomes 1/2 du. I'm going to pull out the 1/2. So I get 1/2 the integral of du over u to the 1/2. Let's rewrite that as 1/2 u to the negative 1/2 is what we're really integrating. Plus 1 times the reciprocal, so 1/2 times 2, and then u to the positive 1/2, plus c, so that's 1 times u to the 1/2. So really, finally, we just get the square root of x squared plus 2x plus 5 plus c. All right, let's take a look at the next question, which has it's a little annoying. All right, use the table above, twice differentiable function f of x to answer. Approximate f prime of 2. 2 is in between 1 and 3, so we will say that f prime of 2 is approximately f of 3 minus f of 1 over 3 minus 1. That's 5 minus 3 is 2 over 2, so 2 over 2, which is 1. All right, now this is where it gets a little weird. We want to prove that f prime equals 0 at least twice. All right, so when I need to do this, what I like to do is I'll go to the table and I'll just do little arrow things. So we definitely know, so let's set it up. We're using mean value theorem, right? F of x is twice differentiable. So I think we should do this. I don't know that we have to, but I always do it anyway, just in case. F of x is twice differentiable. Therefore, f of x is differentiable, which implies that f of x is continuous. So now we know that f of x is differentiable and continuous. We can use the mean value theorem. But how are we going to do it? Well, between -2 and 1 you decrease, 1 to 3 you increase, 3 to 6 you increase, and then 6 to 10 you decrease again. So what I'm going to do is I'll use mean value theorem to find where f prime must be negative, and then positive, and then negative, and then I will use intermediate value theorem to show that f prime must equal 0 twice. That's my goal. So first I'm going to go from -2 to 1 to show that f prime is negative. So it'll be by mean value theorem. I'm going from -2 to 1, and it's just the normal setup. So f prime of, let's say, c1 is f of 1 minus f of -2 over 3. That's -5/3, which is less than 0 for some c between -2 and 1. Now I'm going to go from 1 to 3, where we're increasing. So I'm going to say that f prime of c2 is equal to f of 3 minus f of 1 over 3 minus 1, which is, what is that? I'm going from 1 to 3. That is 2 over 2, so 1. Yeah. Greater than 0 for some c, 1 between 1 and 3. And then I could have gone from 3 to 6, but I went from 1 to 3. I could have gone from 1 to 6. All of those would show increasing. But for the next one, I have to go 6 to 10. So I'm going to say f prime of c3 is f of 10 minus f of 6 over 10 minus 6. I think is -5/4. That is less than 0 for some c3 between 6 and 10. You can see I'm out of space, so I'm going to just import like f prime of c1 is -5/3, f prime of c2 is 1, f prime of c3 is -5/4 to the next page and keep going. So that's what we know so far. So what I'm going to do now is I'm going to try to use the intermediate value theorem to show that f prime equals 0. I know that f prime goes negative to positive to negative. So f prime, if f prime is continuous, must have 2 zeros. So let's establish that f prime is continuous so that we can use intermediate value theorem on it. So I'll say f is twice differentiable, so f prime is differentiable, which implies f prime is continuous. Okay, now we're going with intermediate value theorem. So f prime of c1 is less than 0 is less than f prime of c2. Therefore, by intermediate value theorem, f prime of, I'm going to call it d1, is equal to 0 for some d1 between c1 and c2. That's what you have to do. It's like a lot of, the logic is sound, but there's a lot of logic. And then we're going to do it again between c2 and c3. Just make sure you get the right order, right? c3 is the negative one and c2 is the positive one. So f prime of c3 is less than 0, is less than f prime of c2. Therefore, by IVT, there's a d2 where f prime of d2 equals 0, and d2 is in between c2 and c3. So did we answer the question? We did. We answered at least twice. So f prime of x is 0 at least twice because we showed that it must be. Could be a lot of times, but definitely twice. All right, now the reason I use d1 and d2 here is because the next question is to prove that f double prime equals 0 for some x. Well, if I've shown that f prime equals 0 twice, f prime has the same y value twice, the slope of the secant between those would be 0. So we're using the mean value theorem applied to f prime. All right, so if I'm going to use the mean value theorem on f prime, I need f prime to be differentiable on the open interval and continuous on the closed interval, but we don't really have intervals here. So let's say, apparently I didn't put anything in here, but since f is twice differentiable, f prime is differentiable, and that implies continuous. Therefore, by mean value theorem, f double prime of x is f prime of d2 minus f prime of d1 over d2 minus d1, which equals 0 for some x between d1 and d2. I think that the combination of part B and D of this is actually the single hardest thing to write up a justification for in Calc AB. So it's definitely worth watching that again, making sure you can definitely do it, see the logic of it. Anyway, that's the problem set. I hope this was helpful, and good luck.